This screencast is on electrolytic cells and the types of calculations we'll have to go through in AP Chemistry with electrolytic cells. So electrolytic cells are galvanic cell backwards. This time, instead of producing electrical energy, they use electrical energy to force a non-spontaneous reaction to happen. A very common application of this is electroplating, because normally metals don't run up to other metals and bond to them or stick to them unless we force it to happen. So if we look at the diagram of a galvanic cell, so again, these are our spontaneous ones, we have electrons flowing from our anode to our cathode. This is that zinc copper battery that you guys built, and we have a little voltmeter that's reading at 1.10 volts. If we, instead of the voltmeter, put a battery on there, we can turn this into an electrolytic cell. Now, the battery has to have a voltage greater than that 1.10 volts, and it's going to force, it has to be greater to force the electrons to move the other direction. If I switch back and forth between these two slides, so this is my electrolytic cell, I'll go back to my galvanic cell. If you look really closely, I'm going to switch it back and forth, you'll notice that in addition to the battery and the voltmeter changing, if you look at the bottom at the yellow words, notice my anode and my cathode are switching. So in my electrolytic cell, my copper becomes my anode and zinc becomes my cathode. The electrons are still going to flow from anode to cathode. So we don't have to remember anything different. Electrons always flow from anode to cathode. It's just our designations change. All right, another thing to remember when we're talking about electroplating is that electroplating will happen at the cathode, and that's really, really important to remember. That's where we're going to get ions reduced to their elemental form, and we'll get a metal. So in this case, our zinc electrode would increase in mass because that's where our plating is going to happen. Okay. So we need to know a few of the electricity basics, just dealing with charge, current, and time. Now, we've mentioned charge before. Charge is going to be represented by a lowercase q, and it is our charge, and it is measured in coulombs. T, usually a lowercase t, indicates time. A capital T indicates temperature. So lowercase t is time, and it is specific that it must be in seconds for this equation to work, because a coulomb divided by a second is an amp, and that's what I is our current. Now, you need to spend some time making sure that you recognize what each of these pieces or variables stand for. This equation is given on your reference tables. I know there's not a lot that's given, but this one absolutely is, but you got to know how to work with it. Now, we'll layer in more difficult kind of calculations here in a minute, but let's just work with this current, charge, and time relationship. All right. So I have a couple of practice problems, and you're going to be using that equation of I equals Q over T. Now, you can try and work these yourself. They're not very difficult at all. Just pause this screencast and go ahead and work these problems out, and then you can restart it, and I'll give you the answers. Okay. So with number one, we have a charge of 12 coulombs, so that is my Q, and it passes through in 4 seconds, so that is my time, and I'm looking for my current, which is I. So I is equal to Q over T. It is 12 coulombs divided by 4 seconds, and that's going to give me 3 coulombs per second, which is 3 amps. And sometimes amp is written like this, or sometimes it's just a capital A. Right, and number two, they give us the current. So this is I, and we've got our charge, 10 coulombs, so that's Q, and then we're trying to solve for T. So we need to rearrange this equation, and time is equal to Q divided by I. So coulombs, 10 coulombs divided by 0.5 amps, and an amp is a coulomb per second. So coulombs cancel, and I'm left with seconds, and that makes sense for time. And in this case, it is going to be 20 seconds. All right. In number 3, I have a current. So this is my I, and it's going to flow for 2 minutes. So this is my time. But if you remember, I said time must be in seconds. So just a real quick conversion, 2 minutes is 120 seconds. And now I have that in the correct units, and I'm looking for my charge, which is Q. So Q is going to be equal to I times T. And so that is 0.200 amps, which is a coulomb per second, times 120 seconds is going to give me coulombs, and actually 24 coulombs. All right, that's the basics of working with this equation and solving for the different variables. Now what we're going to do is we're going to show how this is done in electroplating calculations. And then in class, we'll actually do some electroplating. It will involve this equation at some point in time, and then we're just going to combine it with some stoichiometry. Okay. So I'm just going to work with this first one, calculating and plating. So remember that Faraday's constant is 96,500 coulombs per mole of electron. So my first question here says, how long must 5 amps of current be applied to produce 15.5 grams of silver from silver ions? All right, well, if we go back to that formula that we were just working with, I equals Q over T. In this case, they give us I. So we have this one. They're asking for how long, so this must be what we're trying to solve for. In order to solve for time, if I have the amps, the other thing that I need is Q. All right, and those are my coulombs of charge. That's what I'm going to get from a stoichiometry problem. So I'm going to start with my other number here, that is that 15.5 grams of silver. And at this point, you may not know exactly what to do with those grams, so we'll just kind of do what comes natural. If we have grams, when in doubt, mole it out. So let's figure out how many moles we have. The molar mass of silver is 107.9 grams in 1 mole of silver. Okay, now I have moles of silver. My end game is I'm trying to get to coulombs. That's where this statement comes into play. This is going to be a really good conversion factor for me. But in order to use it, I need to have moles of electrons. And if I have moles of electrons, I can convert to coulombs, which is what I'm trying to do here. I don't have moles of electrons yet. I have moles of silver. So that's when I have to pay attention to this part here, or my knowledge of the most common ion formed. So when silver goes to the ion form, it loses 1 electron. And that's important, and that's going to be our next conversion factor. 1 mole of silver is going to liberate 1 mole of electrons. So it won't be 1 for everything, but for silver, because it goes from 0 to 1 positive, it is 1 mole of electrons. All right. So now I have my moles of electrons. Now I can use Faraday's constant, and in 1 mole of electrons, I have 96,500 coulombs. So I'll calculate my coulombs to 3 sig figs, because that's what I started with here. And I end up with 13900 coulombs. So that is Q. And now I'm going to plug that into this formula up here and solve for time. So T is equal to Q divided by I. My coulombs is 13,900. And my I, they gave me in the original problem, is 5 coulombs per second. So coulombs cancel out. My answer is going to be in seconds. So 13,900 divided by 5 is going to give me 2,780 seconds. Now, you would never report that amount of time in seconds. So let's take it to a number we might use. That is also equal to 46.3 minutes. And that would be a reasonable time or answer to this question. The next question is really going to be that same sort of problem. It's just backwards. So calculating the mass of the plated metal. So the first one was how long it'll take. The second one is the mass of a plated metal. You'll either get one of these two types. It tells me I have a current. So this is my I. And it passes through a cell for 14.5 hours. So that's my time. We know that that's going to have to be in seconds. So 14.5 divided by, 14.5 times 60 times 60 gives me 52,200 seconds. Oh, that's a 5. Doesn't look like one, but there it is. Okay, so, and they're asking for the mass of the magnesium that is produced. So in this case, if I have my amps and my time, I can calculate Q. So Q, I'll just do it up here. Q is equal to amps times time. And so that's going to be 0.912 amps times my 52,200 seconds. And remember, an amp is a coulomb per second. So now my seconds are going to cancel out. And my coulombs will be 0.912 times 52,200. 47600 coulombs to give me those 3 sig figs. So now I have my coulombs. Now I'm going to use stoichiometry to convert from coulombs to the mass of magnesium. So I'll start with 47600 coulombs. And the only conversion factor we know with coulombs is Faraday's constant. 96,500 coulombs is 1 mole of electrons. Now we have to go from moles of electrons to moles of magnesium. When magnesium becomes an ion, it becomes an ion with a 2 positive charge. So how many electrons are moving? 2. So there are 2 moles of electrons in 1 mole of magnesium. And that's that new little kind of conversion factor that we have. And now I have moles of magnesium. I need to go to grams, so we'll just use molar mass. It's 24.31 grams of magnesium. So let's see. That's going to be 47600 times 24.31 divided by 96,500 times 2. And I end up with 3 sig figs, so 6.00 grams of magnesium. And those are the types of problems that are associated with electrolytic cells and specifically electroplating.